Right, so we've looked at the alphabet, if you like, of mathematics, that being the numbers and the algebra. Now let's look at the language, the functions. Okay. Some definitions to start off with. A relation. Okay, so a relation. It's a rule that maps between two sets of values. There you go. It's a relation. It's mapping certain x values to y values and vice versa. In fact, it's the relationship x squared plus y squared equals 5. But then we have a very special type of relation that we call a function. And a function uniquely maps from one set of values to another. So something like this. It uniquely maps, because what we're saying is, this x value of -2, there's only one number it'll go to. And the same for every single number in that set. It'll only go to one number. Now, you can have more than one number going to. So, for instance, in this one, -2 goes to 4, but so does +2. So you can have that. That's y equals x squared. Independent variable, if you like, is the input of the function. Which brings us to this thing called domain. Sometimes you see the word natural domain. Basically, it's every possible value that that independent variable can take. So we can substitute it into our function and come up with an answer. Sometimes it's useful to restrict the domain. We're only interested in looking at particular things. An example I've given there is if we were investigating something and the input we were putting in was time, then we probably don't need the negative numbers. Unless we're looking into the past, I suppose you could use negative numbers there. Dependent variable then becomes the output because its answer is dependent upon the input. So it becomes a dependent. The range then is all the possible answers we could get. All the possible output if you substituted every single value in the domain, and that's the range. Which brings up this function notation, how we write functions. So basically we get the independent variable, we substitute it into the function, and we get the dependent variable. So y equals function x. Very, very simple example. Function x equals 3x squared plus 4. What's function 5? So it's saying, well, 5 is the independent variable. We want to put it into the function and come up with an answer, and there it is, 79. Of course, it doesn't have to be a number. It could be algebra. So function a, I'll substitute a in for x, and basically it becomes the same thing. 3a squared plus 4. That one's a little bit boring. This one's a bit more interesting, something like that. Function x plus h minus function x. So we substitute in x plus h, and then we subtract when we substitute in x. Playing around with that. Does anything cancel there? Yep, we've got a bit of cancelling. We end up with 6xh plus 3h squared. So how do we test for functions? How do we tell whether our relation is indeed a function? Now, visually, we've got the vertical line test. Basically, if you draw a straight line parallel to the y-axis, it will only ever cut the function once, if at all. There's an example of a hyperbola. It doesn't matter where I put my vertical line, it will only cut it once. And in fact, at the y-axis, it doesn't cut it at all. But that's fine. That's all right. It just can't cut it more than once. So yes, that is a function. Parabola on its side, x equals y squared. No, because I could draw a vertical line in and it cuts it twice. So if we know the picture, it becomes very easy to tell whether something is a function or not. Actually, this last one here is made up of two separate functions that are joined together. Y equals the positive square root of x and y equals the negative square root of x. Domain and range then, how do we find it? So the domain, again, if you've got the picture, it's the world's easiest way of finding an answer because you just look at the picture and you can see what the domain is. There's x equals y squared. So we say, well, where does this curve exist? You can imagine walking along the x-axis if you like. Look above, look below. Is the curve there? If it is, it's in the domain. So for this one, it's x is greater than or equal to 0. One of these piecewise functions. We get x is less than or equal to 0, but then all of a sudden it stops and then picks up again over at 2. That would also be x is greater than 2. If we don't know what the picture looks like, so we've got to work with the algebra. What are the sorts of things we look for? And we think, well, what's going to cause problems fractions are going to cause problems. Because what do we know? We know the bottom of the fraction can't equal 0. Let's go back to our hyperbola. Let's just pretend, oh, I don't know what that looks like. I look at the fraction and go, well, hang on a sec, I've got a problem here. I know the bottom of the fraction can't equal 0. So the domain for this one is all real x except that value, x equals 0. Remember, domain and range for that matter is an inclusion set. So we talk about what's included, not what's excluded. So it's all real x. We don't just write it as x does not equal 0. That's not a good way of writing domain. We want to know what's included. So everything's included, just not this value of x equals 0. Bottom of the fraction can't equal 0. In this case, I know x squared minus 1 can't equal 0. X can't be plus or minus 1, so we have all real x, except x can't equal plus or minus 1. If I have two fractions, I know x minus 1 can't equal 0, but I also know 7 minus x can't equal 0. So I get 2 points of exclusion in the domain there. All real x except x equals 1 or 7. Root signs also cause problems. Well, probably more the even roots than the odd roots. So square roots, fourth roots and so on, because you can't find the square root of a negative number. So that's going to cause problems. So if I have y equals the square root of 4 minus x squared, I know, hang on a sec, that has to be a positive number. 4 minus x squared has to be a positive number, or 0 of course. Could be 0. Solving that, x squared less than or equal to 4, I get that x is in between minus 2 and 2. In fact, that would be our semicircle. If I have two square roots, again, each one of those has to be greater than or equal to 0. So I know x has to be greater than or equal to negative 3, but also x has to be less than 5. But both of those must be true. Therefore, I must be in between minus 3 and 5. 1 over the square root of x plus 2. I've got two problems here. I've got the fraction and I've got the square root as well. The fraction would tell me the bottom can't equal 0. The root tells me it has to be greater than or equal to 0, but it can't be equal to 0. So in other words, x plus 2 is simply greater than 0. Solving that one, we get our domain. Okay, what about range? Once again, if I've got the picture, life's very easy. I can just look at the picture. This time I'm climbing up the y-axis and having a look either side. Is the curve there? And in fact, it's everywhere for that one, so all real y. Now, when you're writing down domain and range, don't just say all real values or something like that. You need to specify. Range is talking about the y values. Domain is specifying the x values. So you say it's all real x, or in this case, all real y. There's our piecewise function. That one will be y is less than or equal to 1, and y is greater than 3. But we don't know what the picture looks like. So what sort of things do we look for now? Maximum, minimum values. How far up does it go? How far down does it go? Is there something that's going to cause a problem here? Well, here we go. We know even powers, and absolute values for that matter, are always going to be positive. So that's going to tell me something about the output. Y equals x squared. Ooh, what's that look like? Not a clue. But what I do know is x squared has to be greater than or equal to 0. Therefore, the y's have to be greater than or equal to 0. Whereas if I have y equals x squared plus 3, again, that x squared has to be greater than or equal to 0. The y, therefore, has to be greater than or equal to 0 plus 3. We get our range. 5 minus x squared. Well, x squared has to be greater than or equal to 0. Therefore, minus x squared has to be less than or equal to 0. So we're going to be less than or equal to 5 minus 0. 5. Absolute value, but the same idea again, that hang on, that has to be greater than or equal to 0, because absolute value of something is always going to be positive. So looking for those sorts of things. Y equals absolute value of x plus 2 minus 5. That one's got to be greater than or equal to 0 minus 5. Restrictions on the domain. So we might have found our domain, and it might not be all real x. There might be some restrictions in there. Well, is that going to cause problems then with my range? Because now there's certain numbers I can't use or something like that. So to get a feel for range, the idea is, well, just have a look at those endpoints. Where is it there? And then maybe the centre of the domain. They're 3 good points to check. If you're still unsure, well, just plug more points in until you start getting a feel for what the function's going to do. So let's go back to our y equals square root of 4 minus x squared. I was going to say semicircle there, but let's pretend we don't know what it looks like. We worked out the domain was minus 2 to 2. So okay, if I sub in 2, I get 0. If I sub in 0, I get 2. I didn't bother with the other endpoint because I'm squaring the x. So obviously, negative 2 is going to give me the same answer as 2. There's probably a good chance this is going between 0 and 2. because what I do have here is a lovely symmetric curve. So range for this in between 0 and 2. Fractions, okay, they cause problems too when it comes to range. Because what do I know? If I've got a fraction where it's just a constant number on the top of the fraction, then it would be impossible for that fraction to equal 0. You can't divide a constant by a number and get the answer 0. Again, we don't know. What is that shape? Okay, this fraction can't equal 0. Therefore, y can't equal 0, so my range is all real y except y equals 0. 5 plus 1 on x then, same idea. Well, now I know I can't get the answer of 5 plus 0. Therefore, the range all real y except y equals 5. Ooh, x plus 7 on x plus 4. Bit harder to tell. There are different ways we will see to handling this. At this stage, probably just breaking this up into its components. We do a polynomial division, I guess is what I'm saying. If I was to divide x plus 4 into x plus 7, I'd get 1 plus 3 on x plus 4. Well, now I've got a fraction where there's a constant in the top. I know that fraction can't equal 0. The y can't equal 1 plus 0. Everything except 1. So 3a and 3b